today, Professor Caslav Brukner. Professor Brukner, he got his PhD in 1999 from the Vienna University of Technology, and he's professor of the University of Vienna since 2014 and scientific director of the Institute for Quantum Optics and Quantum Information in Vienna since 2021. Professor Brukner is internationally recognized for his works in quantum optics, quantum nanophysics, and quantum information, and probably, I can say this, he's the main name today working at the interface between quantum information and gravity. So today he's going to talk on how does a quantum particle see the world. This stage is all yours. Thank you very much for accepting our invitation.
Thank you very much for this nice introduction. And also, thank you for the invitation. It's a great pleasure to be here. As you already heard, I'm going to talk about a topic that I entitled, How Does a Quantum Particle See the World? And this is the work that has been done together with Anne-Catherine de la Hermete and Victoria Cabell, who are here sitting, also in the 4th row. And they, and together with Esteban Castro, who was a member of our group, is now building his own group in Paris. And I also want to excuse myself for those that might have heard part of these talks or the subject, because we are, so to say, touring through Brazil. And we were in Natal, we were in Belo Horizonte, and in Campinas. And maybe some of you heard that either from me or from Anne-Catherine or Victoria. So I have chosen this title to be a little bit more provocative in the hope that you will come. Now I have to do the hard part of the job and convince you to stay. But at the end of the talk, I may conclude a little disappointing that according to what I understand right now, the world as seen by the quantum particle is not very different than the way how we see the world. And that has to do something about a principle that I would like to promote during this talk, that the physical laws are independent of the reference frame, which we know from the textbook physics, but also independent from the reference frames that themselves may obey quantum mechanical laws, are quantum reference frames. And so that's the reason why we believe that the quantum particle, or if you would be sitting on a quantum particle and describing the world would not be very different in its physical laws. Okay, so my background is in quantum information. I understood that there are many people here coming from the conference on quantum information. But what we do in Vienna, we try to use quantum information and operational tools to address some questions at the interface of quantum physics and gravity. And that's basically where we are here in this intersection for the last couple of years. And there are many topics from this intersection. Maybe you heard about ADS-CFT correspondence. This is not what we are doing, but it belongs to this intersection. And then there are two more topics, which is quantum causality, or quantum or indefinite causal order, which is also part of the conventional quantum information science, and quantum reference frame. And that's the topic that I want to talk today. So before I delve into the subject and also tell you in more detail what I want to speak today, I go back to the title of the talk. So how does a quantum particle see the world? And I take here a picture from a paper published in 2011 by Angelo, who is actually Brazilian, and the co-authors. And so they develop a framework that is initiated, so to say, our discussion in Vienna. I am taking two pictures out of this paper that motivated our work, but in many aspects of the details of their work, I would not, I disagree. but I think the basic idea that was presented there is the core of what I want to tell you. And so here are these two figures from the paper. On the left-hand side, you see here a conventional view from the laboratory frame. So you can think about here as a particle in a superposition that goes one or the other way, and these are the mirrors, and the particle, the photon, for example, would be reflected from these two mirrors, and the two beams will overlap and end up then in the photodetector. And that's a particle in a superposition, a Mach-Zehnder interferometer. And now you can think of how this picture would look like if I were traveling together with a photon. And what they propose is that the picture would be something like that. Then the photon is localized in its own reference frame, and everything external to the photon will appear in a superposition. And that's why this lab is put in a superposition. And OK, so that's a cartoon, but an important one, because if you try to formalize this, you might get something new and may address some questions. And first of all, the question about what I announced is the question, how do the physical laws look like from this new reference frame on the right-hand side? And this has something to do with a very nice idea and very powerful idea of theoretical physics, namely the covariance of physical laws. And what it says is that the laws of physics are of the same form, regardless of the choice of the reference frame. That's a very powerful thing that we use again and again in many different variants in physics. And I give here an example from quantum mechanics that should be familiar with everybody. So what you see here are two reference frames whose origin can be identified with the position of a tree. So there is a one unprime and a prime reference frame. And then there is also an additional physical system, a quantum system, which is in some wave packet, this red wave packet. And now, if we write down the Schelling equation in two reference frames, we can go from the description of one reference frame in another reference frame by suitable transformation that I denote here S, which will also change the Hamiltonian in the prime reference frame as compared with the unprime one. And if this transformation is time-dependent, you will also have this additional term. Now, which transformations are especially interesting for us? These are that we call symmetries. And the symmetries are those transformations in which the Hamiltonian preserves its form, we say. So if we understand the Hamiltonian as a function of momentum and position, then the functional form should stay the same, like p squared over 2m is the free particle and should be free particle in both reference frames. If this is the case, then the S is a symmetry. But all what I'm telling you now, so far, is the case in which we reference frame are really classical. You see, the only quantum thing here is a quantum particle. But in reality, we assign reference frame to systems in our lab. For example, you say, well, this wave packet is maybe 10 meters from the wall of my laboratory. So reference frame are physical systems. And then you might ask yourself, well, if they are physical systems, they should obey physical laws, and in particular, quantum mechanical laws. And that's what this cartoon should suggest. It should suggest that if I am in an prime reference frame, and I look what was the previous reference frame, in addition to my quantum particle, then I will see, if I look it very, very precisely, at least in principle, that this reference frame is also has quantum mechanical features. And therefore, I should assign a quantum mechanical state, not only to the system under consideration, but also to the reference frame. Now, if I do this step, then I can ask questions like, are physical laws covariant under the change of quantum reference frame? Basically, I can repeat the whole story that we know from the symmetries and classical reference frame and extend it to the quantum reference frames. Do physical laws have this larger set of symmetries? It's one question. Or, the other way around, if you adopt the validity of the covariance principle, even under quantum reference frames, can this insight or assumption uncover new physics? Like, we believe that this is true. What should the laws look like then? Okay, and that's exactly the point where I want to continue. So in the rest of my talk, I will try to use the covariance of physical laws under quantum reference frame as an assumption and see if I can address certain problems in physics that have not been addressed yet, or where there is not a consensus how we should address them. And this will be a typical situation in quantum gravity. So what you see here is a situation in which there is a localized object that gravitates, that produces gravitational field, and this is in a cartoon, the Earth. And then there is a quantum system that falls freely in the field of gravitational Earth. That's something which we know how to describe. It might be even hard, but there is a quantum field theory and a curved spacetime that some of you are working on, and can describe this to arbitrary precision of calculations, at least in principle. Now, this is a situation which there is no consensus how to deal with, because now the source of gravity is put in a spatial superposition. Therefore, the gravitational field around this Earth is also in a superposition, and then the space-time metric is not well defined because it's some kind of superposition, and it's fair to say that we don't have a broadly accepted theory of quantum gravity for which we can solve this problem in full generality. Now, what we want to suggest is that we may leave this problem aside and then change a reference frame from what you see on the left-hand side on the right-hand side, because we believe that the physical laws will not change under this change, and then solve this problem on the right-hand side, which could be understood, and then go back. So what you see here is a change of the quantum reference frame. On the left-hand side, the Earth in the superposition. But if there will be a way to sit on the Earth, to localize your reference frame with respect to the Earth, then Earth will be localized, but everything outside of Earth will be put in the superposition, just like we had a situation with the Mach-Zehnder interferometer. So that's the idea. We solve this in the appropriate reference frame, and then we go back and provide the answer without really going through the consideration or assumptions about the details of a quantum gravity theory that we will need in order to solve the problem on the left-hand side. Okay, so that was kind of introduction. And now for the rest of my talk, I will try to formalize this. And I will try to introduce quantum reference frames, then to introduce the generalized principle of covariance, and then go through some applications. Mostly, this will be just quantum translations, what we call. I will mention maybe quantum boosts, and tell you about how to solve this problem that we just defined for the motion of a test particle. I will not go into the time dilation. It will be just one slide to tell you that we can do also that, and then generalize this and conclude. So let me start with the introduction to the formalism. So again, I start with the classical reference frame. And I will adopt the view that was promoted by Menis, but also with Carlo Rovelli, that everything what I can say about the system is only relative to some reference frames. I make only relational statements in physics. So what you see on these two pictures are two particles that are classical particles, the blue, the orange, and the gray one. And I always choose one of them to be a reference frame with respect to which I will define the distances of the other two. And the reference frame will be exactly the one with the flag. So here is a blue origin of the reference frame. And so I have then distances of A and B particle with respect to the blue reference frame. And then on the right-hand side, I will change the view, and I put the flag on the orange particle, in which case the blue one will become an external system to the orange one, and will have corresponding then position defined by this change of the reference frame. So it will become minus XA, where it was the previously XA, the orange with respect to the blue. And also the gray one will get just the relative distance with respect to the new reference frame. Okay, now what we suggested back in 2019 in this work by Giacomini et al. Is to, what I just said, to treat and assume the same transformation to apply also for localized quantum systems. And what I did then in order to do that, to make this step, I just put the cats. But the coordinate transformations remain the same. It's just now the cats. And now, if you look at what you have on the left-hand side, you will see that there is always some kind of a reference cat, 0, because whenever you are sitting on C, C is not any dynamical degree of freedom. It just stays at that 0 point. And all what is the dynamical degree of freedom are the position of the other two particles. And here we write the whole basis for all possible positions of the A and B particle. And now when we move to a new reference frame, we get a whole new basis in a new reference frame where now A is in a 0 reference frame, reference state. Now, if you want to connect the final state with the previous one, what you need to do is to apply certain transformation. And I want to tell you what this transformation is. And the best way to see this is in the 2 steps. The one is the gray step, so to say, where you see that you start with the product XA, XB, and then you get, for the B particle just, the relative distance. And this relative distance can be obtained from the previous position of the B particle if you shift by the generator of translation, which is the momentum of the B particle, for which amount? For the amount where A particle was. That's why here we have XA and PB as an operator. That's the first step. And then there is a second step, which is a blue part, which leaves aside the B particle and just exchange the reference frame between A and C. And so what you see here is that previously I have 0 at C and XA for A particle. And now we have not only exchanged the values of the C and A, swapped the states, but we first also made a mirror operation or reflection of the position of XA. So basically, in order to, from that to come to this state, we apply what we call parity swap. So it first reflects or mirror the position of XA, and then swap the states of C and A. And that's what results exactly in the state what we have before. OK, now the full transformation is a composition of that. And so if you write this composition, you will see that that the first part transforms into something which is a generalization of translation in Galilean transformations, because you move the B particle for the amount where A particle is. But you don't know, it's not well-defined position of an A particle. You have to read out where A is. And when you read out where A is, then you push the B particle. And then you have the parity swap. So this is a combination of 2 unitaries. It's a unitary transformation that transforms states on the left-hand side to the states of the right-hand side. So now let's go. I mean, this was kind of to introduce the operation. But what this operation do, let's look at this. First generalization from these 3 localized wave packets is the B particle is not localized. So it's an arbitrary quantum state. That's not very interesting. You just apply this operation on this state. The B particle is not involved as a reference frame, so it's not really very interesting. What starts to be interesting if the orange particle, that will be next reference frame, is put in a January quantum state. So I put it as in a spatial superposition of 2 positions. You can take any arbitrary state. And what it turns out that when you apply this operation is that the 2 other states, the states of the blue and the gray particle, become entangled. And that's somehow easy to see that there is some kind of correlations, because the orange one could be either here or here. If it is here, then it's closer to the blue one and further away from the gray one. If it is in that dark orange spot, then it's the other way around. So there is certain correlations in the position of the 2 particles, or more precisely, quantum correlations, or more precisely, entanglement between them. And indeed, if you start with the state that we have on the left-hand side, apply this transformation, what you will get is an entangled state. you will, and why it is entangled state? Because first of all, you have different possible positions for the C particle. And depending on this position, you will push the B particle for a different amount. So when you apply these different translations, at the end you will get entangled state between C and B. And that can be obtained with applying this operation on the initial state. Now, one of the main results of this paper and this approach is that exactly what we have seen, namely that superposition and entanglement are not absolute notions, but they do depend on the choice of the reference frame. On the left-hand side, I have something which is a factorized state, it's a product state. At the end, I have an entangled state. So it does depend on the reference frame we take. And so there is a series of examples which have the same feature. And here I list them. On here, left upper corner is the case of the classical reference frame where everything is very well localized. And when I take some point of view of some reference frame, I do not draw really as a state. It's a part of the coordinate system. So this is the point of view of C, where A is very localized and B is arbitrary. And what happens when we change the reference frame, the states remain the same of the nature of the quantum states. They get just different positions. But here is something which we just considered on the previous slide. A is in a superposition. And so when I jump from C into A, C and B will get entangled. But we can also have an opposite situation. And that's what you see here on the lower left corner. From the C point of view, A and B are entangled, like either this or that combination, in such a way, that's the choice, that distance between A and B is always the same, L. Now, if we jump on A reference frame, then B will be on the distance always L, and will factorize out from this entanglement previously, and C will be delocalized. So it's just the opposite of what is happening here. And the last case is basically as the lower left corner, but in the continuous case of an EPR state. And I omit this to explain in details because there is nothing new really physically coming. Now, what I want to tell you now is that what we just learned about quantum translations and about symmetry of translation is not a peculiar case and only one case, one example. We can also think about boosts and quantum extension of the boosts. And well, just to define what it is, transformation between two quantum reference frames which are in a superposition of unitary relative motions with respect to each other is something which we'll call quantum boost. And so here is a situation in which, from the C point of view, you see that A reference frame is in a superposition of two velocities, and then there is an additional quantum system. Now, the transformation that transforms from C to A has a very similar form as in the case of translations, and that's the form. So what you see here is this exponential part, which is nothing else than Galilean boost. So we boost with the Galilean generalization of Galilean boost, the B particle, for how much? For exactly the velocity of A. So this is just the velocity of A. So what was, again, a parameter in the classical reference frame becomes an operator here. So we have an operator. We have to first read out what the velocity is of A, either V1 or V2, and then boost B particle. And then at the end, we have also parity swap. It's only difference to the previous case that what you swap is not the position of two particles, but the velocity of two particles. And so that's another quantum transformation that can be applied in different cases. And in the particular this one, if you really jump on an A, then the state that was written like that, where I omit now 0 reference states, if you jump on the A, the B and the C will get, again, entangled because we will, from the A point of view, have different velocities of C, and that depending on the velocity of C, we will boost B particle differently here and here. So the story repeats itself. Okay, now, having understood what are transformations, quantum transformation, we can ask ourselves, what would be the symmetries? Yes, please.
The velocity of the classical velocity, so the V, they include this slide.
Here will be quantum velocity. The next slide. These are the states already. So these are the cats, so they are not classical, but it's states, it's not an operator. Does it answer? There are many questions. I just warn you that I preserve the right not to answer the question in order to get some time. But I don't know whether this answers first your question. This should indicate that the particle or the reference frame of A is in a superposition of two velocities, just like in that state. There is, I see the index, it should be large A.
May we think of a superposition of momenta?
You can see a position of momenta, which we are here all in a non-relativistic case, is the superposition velocities, Galilean group. Yeah. There was one question here, and then there was another there.
Professor, I have a little naive question. When you just introduce the concept that I think my question is kind of naive, actually. When you just introduced the concept that when we change the reference, we can generate somehow entanglement in the reference frames. In my mind, although entanglement is a non-local interaction, two particles, for example, to reference frame be entangled, they have to have interacted at some previous time to generate that interaction. So how can we associate these things? And it was a little confused for me.
Yeah. I think when you say they have to interact in one previously, you already have chosen certain factorization of the Hilbert space in which the particle was in the product states before interaction. You can also create entanglement by changing the factorization of the Hilbert space. So in my factorization, I factorize them in such a way that what was the product states is entangled. Because this is something what is always assumed implicitly as certain factorization. And what the quantum reference frames do is exactly change of factorization of the Hilbert space. That's why the product states appear entangled.
May I ask just a small question? I don't want to interrupt your seminar, but anyway, you're going to have as much time as you want, almost. My question is...
I'm sorry about that.
Yeah. At this point, you are writing the same state in different ways, but this does not imply that observables are going to change. Am I correct?
They will also change. There's a unitary of, as you see, these the transformations between reference frames are unitary, and you can apply them both for the states and observables, and therefore, anything what describes as a trace rule, as a probability, will remain the same. What will change is the nature of the states, and what will change is the nature of the observables. So, for example, if you measure in one factorization two local observables in order to violate Bell inequalities, in the new refactorization, new reference frame, that will be an entangled measuring.
I see. But the state is the same.
The
state is the same. How you...
The probabilities are the same. Not the states also change from one state into another state.
Okay. May I postpone because, okay? Sorry. Otherwise, it's going to go all the way. Please.
Yeah.
Continue.
Yeah, keep your questions and then we hear later. So why I stopped is to tell you what is a symmetry. And so the symmetry in this framework, or the quantum symmetries, is again very similar as what we had before, namely that we define a symmetry to be that transformation that leaves the functional form the Hamiltonian invariant. So the Hamiltonian will change from the one Hamiltonian, what was before I did reference frame transformation, into the new one, that is the left-hand side. This is when you apply the unitary, how the operator should transform. And if the new Hamiltonian has the same functional form, depends in the same way from momentum and position, I will say this is a symmetry. Now, the only difference to the previous introduction of the symmetry was that when you go from C to A, you change what are the systems. So previously it was A and B. That's why you have A and B. Now, when you transform this, this will be a function of C and B once you jump on A. And what we assume that no matter that you change the particles that you describe with, relative to your reference frame, that functional form of the Hamiltonian is the same. OK. Now, that was the basis. I guess there are still questions. But now let's see whether this has any value whatsoever, in a sense that let's try to use this tool to describe situation that I introduced at the beginning of my talk, namely what I will say in unknown physics. You have a gravitational field in a superposition. And now what I want to say is that I can choose appropriate reference frame, the reference frame of the Earth, such that this situation is translated in something which is known physics. And in order to do so, I should assume that the laws of physics do not change if I make the change of reference frame, but now quantum reference frames. And that's the basis for the generalized principle of covariance, which is formulated in this paper. And I read these physical laws retain their form under quantum coordinate transformation. So not only classical, but also quantum coordinate transformations. And now what I will do, the next, I will try to use now this tool to solve the problem, starting from situations that we had, like in case of the three particles. But now I have a more physical systems. And so I have the previous reference frame R, which was in the previous slides C. Then I have a new reference frame, M, for the mass. That was A in the previous slides. And I have also additional pro-particle, which was B, and now it's S for the system. And now I have this as an initial situation. Then I will do with the reference frame transformation that transforms the original reference from R to M, this situation in which mass is localized and everything else is entangled. Then I solve this problem because I know how to solve this to the extent that we can use, in general, quantum field theory in a curved space-time. And I will see that the particle in a superposition would fall under some, let's say, in some approximation, a superposition of geodesics. And here I do not draw R. And then I go with inverse transformation into initial reference frame, in which this physical law will be described as one localized at the beginning pro-particle falling in the superposition of, let's say, geodesics in some approximation in the field of a mass put in a superposition. OK, so now I just do that, what I just explained. That's exactly the situation that we described with ABC particles. The mass is in a superposition. So we know how to go. We go into the new reference frame in which R, the old reference frame and system will be entangled. And then this is the same state. Then in this reference frame, I solve the problem. And now we can choose different methods to solve this problem. And what we have chosen here is the most simple one, which is due Stodolsky, which he says that if you, in some certain semi-classical approximation, you can treat then, in this new reference frame, the system to obey geodesics. But we go not only into single geodesic, but also superpositional geodesics. So what we omitted, what we do not describe, is dispersion of wave packet along the geodesics. So if you want, you can do that as well. But here is just a matter of principle. So we take a superposition of semi-classical trajectories. And in addition, there is some phases that will be accumulated corresponding to the time, the proper time difference along the two geodesics. And now we solve this in this semi-classical approximation in the picture 3. And then we go back with inverse reference frame transformation. We go back. And so from the third picture, we go to the fourth picture of the original reference frame R, in which the original reference frame R factors out. It's actually not important. It's used here to provide the unitarity of this transformation. And we end up with a state that describes falling of a single probe particle along two geodesics in superposition. And these geodesics the position of a particle will be entangled with the position of the mass. Because if I'm along this, if I fall along this geodesic, then the mass is here. If I fall along this, then the mass is here. Okay, so that with additional phases that are corresponding to the proper time differences give me the final solution. And that's the way how you can employ this principle to solve a problem that was maybe at the beginning not clear how to solve it. Of course, you can go in the higher order of approximation, not have semi-classical trajectories, which will involve more serious calculation, but the principle will be the same. Okay, now, what I want to say is that Hamiltonian preserves its form under this quantum reference frame. So this is a problem where we would say quantum spatial translation is a symmetry of the problem, because at the beginning, or at the end of the second reference frame, we have a free particle and some gravitational potentials for the particle in the vicinity of this mass. If we go into the original reference frame, we have the same form. It's the same form, it's just that now we have a difference between these two positions. So this Hamiltonian preserves its form under quantum spatial translations. Okay, that's what I said that I will not talk about. And so I just tell you that, because I don't want to keep you infinitely long, that the same structure, the same idea, can be applied also if you want to think about clocks instead of the test particles. So what we here have is a situation where we put a mass in a superposition, and then we have a clock. And we ask ourselves how this clock will tick in the vicinity of the mass put in the superposition. And we say we don't want to answer this directly. We go into the new reference frame in which this clock is in a superposition. Then we know that the closer the clock is, the slower the ticking rate is, according to the gravitational time dilation. And so you see here the difference in a ticking rate of the clock being closer or further away. That's only one clock. That could be in one or the other position. And then we go back, and we solve this problem. And I don't go through this computation because it's a lengthy one, but it provides, it's the same tool. Maybe what is interesting, if you look at the numbers that you get, they are really discouraging for all the experimentalists who are present here. But so even if you put something of 10 to minus 8 kilograms at the distances of 10 to minus 5 meters, and you wait for the duration of an experiment to be 1 second, the time difference accumulated, the proper time difference accumulated is 10 to minus 32 seconds, which is an extremely small number. However, I want to have two remarks about that. The first one is that although it's very small, this effect is still closer to our experimental accessibility than the Planck time, which is 10 to minus 44 seconds, where the people expect to have quantum gravity effects. So from that point of view, that's something, a low energy quantum gravity effect, and that's why it's closer to accessibility, to what we can access. Of course, still very far away. And the second one is that what I want to specify here, that this situation actually describes the genuine superposition of space-time. And the reason for that is that if you have a single clock in your laboratory that is localized, and nevertheless, although it's infinitely well localized, at least in approximation, and it still shows the superposition of ticking rates, the only reason why it can show the superposition or indefiniteness about the ticking rate is because the space-time is in superposition. It is, of course, possible to have the same effect of the clock if it is delocalized in a definite space-time. But if it's localized, it can only be because the space-time itself. And if you see that it works with any possible clock, that's a universal effect, and then we assign this not to the property of the clock, but the property of the space-time itself. Okay, so this is possibly, in my view, the most important slide. And it shows comparison between the model that satisfies general covariance with two other non-standard approaches to quantum gravity. The one is the semi-classical gravity, the other is the collapse model. And now, what we describe here in this lower and upper picture is the same physical, is the situation from two different reference frames. So here the Earth is localized, and the probe particle is put in a superposition. Now, semi-classical gravity states that gravity is sourced by the average value of gravitational field. So the Earth, the gravitational field of the Earth is exactly the average or the mean value of the gravitational field, no matter how the Earth is distributed in space. Here it is localized. So it's really the center of the gravitational field. The source is in the center. And we put two particles exactly at the same distance left and right. Sorry, one particle in a superposition. Now what will happen is, also according to semi-classical gravity, that the particle will start to fall towards the mass. Okay, now let's see and look this from another reference frame. And then this another reference frame, we are sitting on a probe particle. So from the point of view of the probe particle, it is the mass that's in the superposition. But now, the mass produces, the large mass produces the average gravitational field. So it is average from being left or right. Exactly in the middle is 0. So the probe particle will stay still there. That's a different phenomena from the lower one, in which we have approaching the two objects to each other, and here standing still. So that means that this semi-classical gravity does not obey a general covariance principle. And the two stories do not match as a physical phenomena, meaning the laws are not the same in the two reference frames. The same appears for the collapse models. The lower picture is the same as before, and the collapse models are such models in which, according to some scale, let's say the mass, superposition is not preserved, but will collapse. However, the parameters are chosen in a clever way that the small objects can preserve very long in superposition, but big objects cannot. So we put first in one reference frame the small objects in the superposition, and it preserves the coherence. And you can measure that the coherence is preserved. However, if we jump on a small system and look the same situation from another reference frame, where the mass is in a superposition, according to this model, it should collapse. So we will have a 50-50 possibility either that the particle will be attracted to mass because the mass collapses on this amplitude or on that amplitude, which is, again, a different phenomena, and therefore, collapse models do not obey general covariance principle. Only those theories, and that's more or less quantized gravity in this semi-classical limit, that obey general covariance will not distinguish between these two situations, and in both situations we will see attraction between the small and the big object. So this is almost everything what I want to tell you. Now, just one more thing is about generalization. You can think that, well, we did it for one mass in a superposition. Is this so powerful that we can think about any possible superposition of configuration that source gravity, like these two? You see that these two configurations are not the same because the relative distance between, I don't know, Mars and Earth is not the same as here, or Jupiter and Earth. And so if I have a superposition of the configuration on the left-hand side, on the right-hand side, and a produced gravitational field, can I find a clever reference frame so that when I jump on this reference frame, I will have a definite gravitational field, a definite metric? And the answer is no, exactly for the reason that I explained. You cannot put these two configurations by rotations and translation, you cannot put one on the top of each other. Only if you would be able to put each planet on the top of the same planet in different configurations, then you will have the produced gravitational field and metric equivalent in both situations. And this is not the case if they are not related to each other through some global translation or global rotations. So only if this is the case, these two things are preserved, we can put one on the top of each other. Now, you might think that this is then very trivial because these are all identical physical situations that I cannot even distinguish between them, because if I can put one on the top of each other, how do I know that they are different? And they are different situations, although they look the same from the source point of view, because they are pro-particles that make the situations different. The pro-particle can be here closer to the Jupiter and here closer to the Earth. So although the sources of gravity are put on each other, the two physical situation with events, including the pro-particle, are not what we call diffeomorphism related situation. So the pro-particle breaks the symmetry and makes the whole thing interesting in the first place. And there is a generalization in this paper. And I'm coming to the conclusion and outlook. So it will be interesting to formalize the most general quantum reference frame transformation. Going into the relativistic regime, there are some papers also, including our group, going into the relativistic regime, also to the quantum fields. That's the first paper that the same list of authors put recently, where we have two metrics that are not diffeomorphic related, but are related through the conformal transformation, and they are put in the superposition. And again, we can find the appropriate quantum reference transformation in which the metric and the space-time becomes well-defined. So, and that's the first paper where we go beyond mechanics and work with the fields. But that's just first paper. There's a lot to be done on that front. And then another restrictions of our approach is semi-classical approximation. All what we are discussing so far were configuration of mass that were semi-classical and superpositional semi-classical. So I said, so for example, we don't consider dispersion of the wave packet of the Earth, but we treat it classically. And then, of course, it will be interesting if there is a way to test this principle, general covariance principle, in the lab. And there is certain difficulties because we are bounded to laboratory reference frames. So how should we, it's a conceptual also challenge, how should we test that the laws of physics as seen from the quantum particles are the same? And so here is the summary of my talk. So we try to base predictions about situations in which the metric is not well defined, is in kind of superposition or gravitational field, using general covariance principle and being agnostic about really the nature of gravitational field. We didn't solve this. We just say, oh, let's go into another reference frame, and then we can solve this and go back. And so we are agnostic at the beginning of this path, and then get some results. For example, the particle moves in a superposition of geodesics entangled with masses, or the clocks will tick in a superposition of proper times entangled with a mass. But the same phenomena could have been obtained if we would put the cats on the position of the mass, or in a certain sense, in this semi-classical limit, we would treat sources of gravitational field with the quantum states, and that will be some kind of independent reason to support the view of the quantum nature or non-classical nature of gravitational field. And with this, I want to thank you for your attention.
Questions?
I have two questions. The first one is related to time dilation. If you
Are they connected?
No, they are independent.
So make your first, and then we'll come back and make your second.
Okay. If you have a particle that is in superposition of velocities, and you jump to another reference frame, you have the phenomenon of time dilation. So you could like measure 2 times, right? So this would imply that you have a time operator or something like that, but I know that if there was, it would be anti-Hermitian. So how does that come along?
So I would say there are 2 things that you ask. First of all, you referred to special relativistic time dilation, which I was not talking about. But if you would have in a quantum boost also system as a clock, and you jump in another reference frame, which is in a superposition of boosts, indeed, you will have a superposition of special relativistic time dilation. Now, but then you connected this with a problem of time operator. Here we don't talk about time operator. We use, we count the time as we do it in the lab. What we do is we look at some system and some observable that could be maybe spin processing or Rabi oscillation of atomic clock. So it's not a time operator, but it's another physical observable that we can measure. And we then look at phenomena relative to the ticking rate or the oscillation of this observable on the atomic clock. So it's really avoiding the problem of time operator, but using other system. It could be position, momentum, spin, rotation that serve to observe the evolution with respect to the rotation period of these systems, for example.
I have a I have a question because we relativists, we use the word reference frame. In general, just to say that we are using some coordinate system on a space-time. And then, for a relativist, changing reference frames or maps cannot change the physics.
Yes.
But if and on the top of it, we used to assume different observers, whatever is the coordinate, the reference frame, independently from the coordinates. But if I understand your talk, when you say that you are changing reference frame, you are also changing the observer. Am I right? The observer that is going to do the experiment. This is why you can change the reference frame, and this can imply in different observers.
Yeah, ideally.
Am I right?
Yes. Ideally, you will have another. You will have a measurement apparatus assigned to this other reference frame.
I see.
In that sense,
I see.
you perform, if you want, measurements.
I see.
On which basis you will assign the states.
I see.
And measure probabilities.
This is like, for example, making the Bell inequality experiment, the usual one, but with polarimeters moving with respect to each other. This is going to change the result, although the entangled system is the same. Isn't it?
I didn't follow. Sorry. Can you repeat
let us assume that rather than repeating or performing the usual Bell inequality experiment with 2 polarimeters, we move these polarimeters. We move with respect one to the other. We put this we give some velocity. So this is going to change the result.
Okay, so maybe I contribute to this confusion.
Okay.
So here is important, but this is really important point. So I said that this unit transformation, they will not change probabilities. So imagine that in one reference frame, we perform the experiment, and we also, in this experiment, measure something. So we get the statistics.
Mm-hmm.
This will not change. The same experiment can be observed from another reference frame. So this is the same experiment.
Right.
However, I will interpret this experiment differently from if I'm in the superposition of boosts or something like that. Nevertheless, I will get the same results. So, but I will say, no, what you think you measure this observable, for me is a different observable. What you thought that is your state, it's different for me. But
I see.
nevertheless,
The interpretation is different, but the numbers are the same.
exactly.
Okay.
Thank you for Professor. Your presentation was really interesting, really good. What I'm curious about is that when you change to a reference frame in superposition, you create a lot of entanglement. But is coherence preserved when changing reference frames?
It is. So because it's a really, let's say, unitary transformation, so what was the phase between state of one system will be the same phase, but between two products of entangled state. So the coherence is preserved.
I'm quite curious about what would happen if you try to imply the path integral formalism. Like, can you obtain something interesting? I don't know.
I think it will be useful to extend the quantum reference frame transformation to the path integral. That's maybe a way to go to the quantum field theory picture. It hasn't been done yet. I don't think that it will be an important tool, but at least in the quantum mechanics, we believe that all these formalisms are equivalent to each other. So I expect that at least in that domain, it will be equivalent in the results. Perhaps if you want to go beyond non-relativistic mechanics or mechanics relativistic, you should do that.
When you have a superposition of masses, do you consider interaction between the masses themselves? And if you don't, why shouldn't you? Could that both solve the semi-classical approximation, because the two Earths would come together, and also kind of go against your suggestion of changing to a reference frame where there is no such superposition?
It's an excellent question. The same question we got from the referee. I hope you were not the referee. This person was not very kind to us. But it's a good question. So there are two possible ways. There are possible ways which are which preserve linearity of quantum mechanics. And so if you want to talk about terms that people in many worlds like, these two branches do not talk to each other. There is no interaction. There is interference, but no interaction between different branches. So if you want to introduce this, that would be a nonlinear quantum mechanics. And one explicit example of this is a so-called Schrödinger-Newton equation, in which you treat these two masses to interact, and then you will slowly have a collapse because they interact with each other. So if you put a large mass in a superposition, you have nothing in the world whatsoever. They should come together at one point. But then in nonlinear quantum mechanics have many problems, and you have to probably add some terms to preserve, not to have these problems which are related to signaling and so on. But it's a possibility. And this is, after all, something which people, also Penrose is doing sometimes this and so on. I think that I think philosophically the distinction is the following. In one case, you believe that there is a space-time in which mass is just a field put on this in space-time, and then even if it's superposition, this field interacts or self-interact. The other thing is this is a superposition of space-times. There is nothing on which these masses live both at the same time. But yeah, we take an assumption that it's linear. And you're right, this will be violated. The general principle will be violated if this is the case, what you suggest.
Thanks, Caslav, for the very nice and provocative talk. So you see that people stayed, so you managed. So I was wondering, like, if there is any connection between these quantum reference frames and the measurement problem, like the Wigner's friend paradox, in the sense that you also have two observers, and in the end of the day, like, they have two different descriptions, but there you do have different outcomes. Like the experiments actually can be, they are different. So I was just wondering if there is a connection, or if in a certain sense, if you violate these local friendliness inequalities, this wouldn't be like a violation of this general covariance principle. So is there any connection between these things?
So for very long, because our group is interested in both problems, we follow this quantum reference frames also for the reason that we thought this can be help in the solving so-called Wigner's-Friend paradox, just for everybody to be the same page. This is the situation in which you have one observer performing an experiment, and then there is another observer that looks the whole experiment of the first observer. This another is super observer that describe the whole measurement procedure of the first one as a unitary transformation. And so I don't know the answer to your question, but we are more and more convinced that they are not related to each other. And the reason is exactly what I just answered to George, namely that in the quantum reference frames, the measurement is the measurement for everybody. Whereas in the Wigner's-Friend situation, what was the measurement for one person was not, I can still not measure, just unitary transform, is not a measurement for the other one. And so we couldn't find relation to each other. We've tried many things. We tried to get some view from the Wigner's-Friend point, but we failed. Maybe there is still something.
Thank you, Professor, for your presentation. So, since we're talking about Wigner, I'd like to say that Wigner's theorem states that the transformations can also be anti-unitaries.
Anti-unitaries, you said.
Oh, yeah, anti-unitaries. So, is there, have you ever considered about an anti-unitary transformation? Does it, it break some other law that you're talking about? Can it open some paths to work with? Thank you.
That's actually an excellent question, and we should do that. But I mean, there are discrete symmetries that are related to anti-unitaries, and one can think about superposition of discrete symmetries. It will be a nice project.
We have another question here, but I'm sure that there are other ones. So I propose that we stop after this question, but those interested in making other questions, like me, for example, I invite you to stay in the auditorium rather than going to the coffee place. So there's a competition between coffee and physics, right? Very hard competition. And so let's do it, okay?
Thanks a lot for a very nice talk, very interesting talk. I would like to go back to the question about the coherence, but now think the following. When we are in the reference of the Earth, we see a quantum particle in a superposition. But due to the interaction of this particle with the environment, there is the decoherence. So the coherence is destroyed. And the time the coherence is destroyed depends on the number of particles we have in this quantum system. In this case, a single atom, right? But when we move to the reference of the atom, we see the Earth in a superposition, right? But again, the time the coherence, the superposition of the Earth is destroyed, depends on the number of particles we have in the quantum system. That now is the Earth, which is really big. So the decoherence time is different in the different frames. Is that right?
No. Okay.
Why?
yeah, it's a good question. It's a good question. Okay, so what is decoherence? Decoherence is entanglements with some other degrees of freedom. So in order to see that the formalism is right, you should include all degrees of freedom. I didn't do that because it would be making problems. But imagine you said, okay, so let's start with the situation in which mass is in a superposition. And you're right, there will be, in every physically relevant situation, the mass, there will be the air molecules or whatever will start to get entangled, the position of the mass with some other degrees of freedom. What the formalism tells you then go from this reference frame in which you include all degrees of freedom into the one which will localize all of them, and then the particle will be in a superposition. So it's really the same, what the quantum reference frame transformation is the same physical situation. You are not allowed in one reference frame to trace out and the other not. You have to incorporate everything, and when you incorporate everything as unitary, then you apply the transformation. And now you can, then you have in both reference frames the correct pure state. And then you can say, but I'm not interested in whole thing. I will trace out. But that comes later, so to say. I don't know whether this was...
Yes, but it's very surprising for me because a really big system can have the same decoherence time in the end.
Yes. It will be decohering in both reference frames. Okay, in one reference frame, you are sitting on Earth, and you have other degrees of freedom. And the other one, you are sitting on the other, and it's still decohering. It's just transformation from one reference frame to another. It's not a different physical situation.
Yes, I agree. We have to see the same physics, of course.
Yes.
But changing the reference frame, you can see on Earth with a superposition for a really long time compared to this side.
Let's discuss this later.
Okay. So we can discuss it. So stay in the auditorium, please. So let's thank again Caslav Brukner for this seminar. Let's wait 2 or 3 minutes for,
So just an announcement, starting tomorrow, unfortunately, everybody has to wear a mask to be in the IFT. So if you didn't bring one today, you'll need to bring one tomorrow.